So what makes cesium that favorable?
Right. Why cesium?
Other atoms.
Well, remember, it was decided in 1967. So it was before laser cooling and really before there were decent lasers. So why cesium? Okay, a number of reasons. One is so heavy. And for reasons that I don't understand, but I'm sure some condensed matter physicists understand it very well, you don't have to heat it up very much to get a decent vapor pressure. So it's a solid at room temperature, but it melts, not very hot, and you get a decent vapor pressure. So that means heavy and not very hot, the atoms are going slow. So that's good because we don't want the atoms to go
when
fast.
you evaporate them, they will already like you don't have to heat them.
Don't have to heat them very much.
Cesium is like a soft metal, right?
Soft metal,
it doesn't
easy
have a
to
strong
get out,
crystal
checked
lattice.
atoms.
Yeah, but gold is a soft metal and it has a very high vapor pressure. So that's not the whole story.
That's a good point.
And I'm sure people understand this, but I don't. It's one of those things. I would love somebody to explain why cesium has such a high vapor pressure and gold doesn't. But
I think being okay, I can maybe explain this. This is not fact checked, but probably gold is malleable.
It is malleable.
But it has a strong lattice. It's probably more about like the defects and things like that. I think cesium and lithium and these like first, column periodic table metals just don't stick to themselves that much.
Pure gold is
Something
quite
like that.
soft.
Yeah.
You can bite it.
Yeah, but that might be more about the defects, like that the crystal structure can slide over itself.
That might be. I mean, it's
rather than like that you can tear it apart.
It could be. It's obviously both of these things are polycrystalline. We're not not talking about single crystals of any of these. So I don't know.
Yeah, that's true. The softness is actually probably just I brought that up, and that's probably just irrelevant. That's actually like the
maybe I don't know. I mean, obviously, there's something having to do with what the
just the bond strength between
it relates to the heat of vaporization and things like that, I guess. Well, anyway, so that means the cesium atoms that you make the atomic beam out of are going fairly slowly compared to if you did this with, say, hydrogen, which would be, a disaster. Plus, of all the alkalis that are not strongly radioactive, I say strongly because rubidium's a little bit radioactive. Not much, got a lifetime of the age of the universe. It's got the highest hyperfine frequency. As you make the atoms heavier, you get a bigger hyperfine frequency. It's probably just a matter of the wave function having higher density.
I think I've just generated another stupid question. So why don't we just use radiation as a clock? Why do we need this? Seems all very complicated. Why not just use a Geiger counter and watch, the decay? Because that's also should be quite predictable, right?
Okay. Well, if you could imagine using the rate of radioactive decay would be a bad clock because for one thing, it's stochastic. So the rate at which I get counts is random.
But what if you have a very big chunk of...
Sure, but that means it's only going to get better like the square root of the number.
Right, I see. So you need an enormous chunk of the material.
I mean, you wouldn't be able to lock a single frequency to it and then distribute it because it's still coming at random.
Yeah. Okay.
Now
you can measure over a long time, right? Like if you were going to do like a day, right? You would get a lot of counts over a day.
But it's so much easier to do it than when we are doing it.
Now that we have the atomic clocks, yes.
But you aren't too far from something that's really interesting, and that is we're now thinking about using nuclear energy levels as the clock frequency. So now, we started off talking about hyperfine. That's orientation of the spins.
Yeah.
Today, we're talking about, we haven't talked about, but today we're going to move to optical frequency standards. These are actually electronic excitations. So putting the electron in a different orbit, and that's going to produce optical frequency. So instead of being microwave at the order of 10 to the 10 hertz, we're going to be talking about optical, which is a few times 10 to the 14 or 10 to the 15 hertz. That's what the new clocks are going to be. But nuclear transitions are even higher. I didn't really quite get to why do I want the higher frequency? Because if there's anything messing up the performance of the clock, let's say a little magnetic field, shifts things a little bit, I want that to be a smaller fraction of the clock frequency. So I want a highest possible clock frequency.
Just having something high energy protected from noise sources that are...
Well, it's not so much that it's protected.
Well, it's just
But
less. The
it's just
contribution
less,
is smaller,
fractionally less of a
Yeah.
problem. So, so anyway,
How do you
where's it
affect the
going?
nuclear energies? Like, how does that even work?
You can do it with a laser,
Okay.
but only just like recently, like in the last few months, they've done it with a laser. They've excited a nuclear transition with a laser.
Also, aren't we not limited by the width of the sources which pump the laser, which pump the atoms? Like, for
Yes,
example.
and there are. Well, actually, there's only one transition that's any good in thorium. There's a gamma ray. And I say gamma ray not because it's such high energy, but because it's a nuclear transition. So there's two isomers of thorium. One of them is a few electron volts above the ground state. So that produces a photon that is higher than these optical photons, right? It's in the ultraviolet. I don't know whether it's called extreme ultraviolet, but anyway, it's low enough that you can multiply a visible laser up and use the harmonic of visible laser to excite the nucleus. And they've just done that a few months ago. And everybody's excited about it, but it's so far in the future. We got so many problems we're going to have to solve for that we're not even thinking about it as a candidate for the next definition of the signal.